G'day team, welcome back to yet again another video. Today we are going to do a bit of a deep dive into differential calculus. Now I do have a playlist that is a bit of an introduction to differential calculus, so make sure you go back and watch those videos before jumping into this playlist. But today we're going to jump into doing some more difficult questions to do with first principles and bringing in some surds and fractions along for the ride. Now, in my introductory videos, I go through this diagram in a lot more detail, so make sure you go back and have a look at that. But essentially what we're going to be looking at is when we have a function and we want to find the derivative. So if we've got a function y equals f of x, then the derivative of that function is f dash of x or dy by dx, and it's equal to the limit as h tends to 0, okay, of f of x plus h minus f of x all divided by h. Now, at face value, if we applied this limit, we'd get a 0 in the denominator, which we cannot do. So what we need to do a bit of algebraic rearranging or expansion factorization in the top that will allow us to cancel out this h. And that takes many different forms, and we'll go through 3 different examples today. So the first example we've got is find f dash of x by first principles if the function f of x equals x cubed plus 2x. Now, the first thing we need to find is f of x plus h. Now, to do that, we take our original function and we replace every x with x plus h. So I've got x plus h cubed plus 2 times x plus h. And that's all I have to do for this step. So now what I want to do, I want to put it into my first principles formula. So f dash of x, my derivative function, is the limit as h tends to 0 of x plus h cubed plus 2 times by x plus h. Then I have to subtract my original function, so minus, in brackets, x cubed plus 2x. Now those brackets are super important because it's important that that 2x also is negated. And that there is all over h. So like I said before, we can't apply our limit right now, but in the top, there's a lot of expansion that we can do. So I'm going to do the binomial expansion of a cubic with my x plus h cubed term. So that gives me x cubed plus 3x squared h plus 3xh squared plus h cubed. Then I'm going to expand out this bracket here. So plus 2x plus 2h. Then I'm going to apply the negative to both of these terms in this bracket here. So negative x cubed minus 2x. And that is still all over h. So it's pretty long, but what we'll notice is a few things will cancel out. So x cubed and minus x cubed, they cancel out, so I'll cross those out. And then I've also got 2x minus 2x, so they also cancel out. So 2x and minus 2x. Now you'll notice every term that's left has a h in it. So in this next step, I'm going to rewrite the equation with all the crossed out terms gone, but I'm also going to take a factor of h out from each remaining term. So that means I'm left with 3x squared plus 3xh plus h squared plus 2. All right, so that is taking a h out of all those uncrossed out terms up here. And that's still all over h. So now I've got a factor of h on the top and the bottom. They cancel out to be 1. So I'm left with the limit as h tends to 0 of 3x squared plus 3xh plus h squared plus 2. Now if I apply my limit, I'm not going to do anything wrong. I'm not going to divide by 0. So I can treat it like I'm substituting in 0 for h, and I'm left with 3x squared plus 2. So my derivative is 3x squared plus 2. That's a pretty basic example, a little bit more complex than in my previous first principles video, but probably the simplest that we're going to do today. So the next one we're going to do is finding the derivative by first principles if f of x equals 4 times the square root of x. So again, we need f of x plus h. So that is going to be 4 times by the square root of x plus h. And again, let's put it into our formula. I'm going to speed through a little bit of this sort of stuff just because it is a bit boring to watch over and over and over again. So if I do go a little bit silent, just bear with me and I'll keep talking as I go and keep progressing. So f of x plus h is what we just wrote there, minus f of x, which is minus 4 root x, all over h. Now, to deal with square roots, we want to get rid of those square roots. And a way we do that is by timesing by the radical conjugate. So I'm going to times top and bottom by my radical conjugate, which is just the same terms, but we change the sign separating them. So you can see my minus has turned to a plus. And I'm also going to times the bottom by the same thing, because that ensures I'm not changing the value of my expression, I'm just timesing by 1. Now on the top, oh, I'm still in red, on the top we can see that I've got a difference of 2 squares expansion that I can do. So I'm going to square the first term. So that means I've got 4 squared, which is 16. And then the square root of x plus h squared is just x plus h minus 16x. So squaring that term as well. All over h. And then that's just going to be multiplied by all of this stuff here. And I'm going to leave it in its factorized form. And you'll see why in a moment. So 4 root x plus h plus 4 root x. Now, I've got a bracket in this top line that I can expand out. So that will become 16x plus 16h. So the limit as h tends to 0 of 16x plus 16h minus 16x all over. And I'm going to cheat a little bit and I'm going to duplicate that just to save a bit of time. So the bottom did not change. So again, we see a little cancellation. We can do 16x minus 16x. And we can also see I have now left over factors of h. So I can also cancel those out to be 1. So now in the top, I'm left with just 16. Then on the bottom, I'm left with 4 square root of x plus h plus 4 root x. Now, if I apply my limit here as h tends to 0, the denominator doesn't become 0, so I'm allowed to do it. So I'm going to make all h's 0, so that means I'm left with 16 over 4 root x plus 4 root x. These are like terms, so on the denominator, I've now got 16 on 8 root x, and I can simplify 16 over 8 to be 2 over root x, which is the solution we require. So my derivative f dash of x is 2 over root x. All right, let's keep plugging through. So that's a pretty tricky example, and we'll do one more tricky example where we involve a fraction. So let's find f of x plus h, which is 1 over x plus h. So let's throw that into my first principles formula. So the limit as h tends to 0 of 1 over x plus h minus 1 over x all over h. And now you can see we've got fractions in fractions, which is really frustrating when you're first looking at it. What we want to do is we want to write these top 2 fractions as one fraction, so under one denominator. And the way we do that is we cross multiply. So we multiply the first diagonal, and then we multiply the second diagonal, and then we multiply the denominators. So we're going to do that now. So the limit as h tends to 0, I've got 1 times by x, so 1 times by x is x. Negative 1 times x plus h, so minus 1 times by x plus h, that bracket is really important, all over x times by x plus h, so my 2 denominators, and that is still all over h. Now, when we've got a fraction in the numerator divided by one more thing, the denominator in the top fraction and the denominator of the overall fraction are just multiplied together. So this becomes the limit as h tends to 0, x minus h, so expanding that bracket, all over h times x times by x plus h. Now we can see that my 2 x's cancel out, And again, I'm just left with a factor of h on the top, so I can cancel that out with my h below. So the limit as h tends to 0, I'm just left with -1 on top. And on the bottom, I'm left with x plus h. Now, if I apply my limit, I'm not going to make it undefined. So I'm going to substitute in h or 0 for h. So f dash of x is equal to -1 on x times x, which is -1 on x squared. And that is the result we were after. Hopefully this sets you off quite nicely for some tricky first principles problems. They always pop up, so it is important that we are constantly practicing that skill. Thanks for watching, and we'll see you in the next video.